So precipitation reactions. Hard water. Isn't that a funny phrase? What makes water hard? We're soft. How can water be soft, right? It's a liquid. Hard water has dissolved minerals in it, and soft water has much fewer dissolved minerals. Soft water, like they have in San Francisco, that comes from surface water, is not the same as deionized water, but it has many fewer dissolved minerals. Here we get our water from wells underground, and so rain has percolated through the soil and down into the aquifer, and it picks up a lot of minerals as it goes through. So especially out in the country, you get well water, and that water is hard, and it tastes different, and it reacts with soap differently, and it leaves white deposits all over your bathroom fixtures, right? So it's the calcium and magnesium that cause most of the problems. And as this picture shows, you've probably seen this happen. There's this like film around the edge of the sink or the bathtub, right? Bathtub ring. What is that? Well, it's a reaction between the soap that you use to wash yourself and calcium and magnesium ions. So in the bathtub, it's annoying. In the laundry machine, it's a little more than annoying because that scum gets on your clothing, right? And it's got kind of a gray color that makes all your whites really dingy. So laundry detergents are different than soap. They have sodium carbonate in them. And the sodium carbonate will precipitate out the calcium and the magnesium, because calcium carbonate and magnesium carbonate are insoluble ionic compounds. So what happens is the carbonate from the detergent meets up with the calcium ions and forms a solid. And so then this calcium is not available to make soap curd with the soap. Any questions? So precipitation reactions, those are two precipitation reactions, but precipitation reactions in general are reactions in which a solid forms when two solutions are mixed. So this is a solid forming that wasn't present before, and that solid's called a precipitate. And we've done a couple of reactions in class where you mix two solutions and it looked like snow formed, right? And it kind of fell down. Sometimes it was white, sometimes it was blue or black, but it's a solid forming inside of the liquid. So here we have a photograph of a precipitate forming. This one's kind of a bright yellow color. So what's happening here is we're mixing potassium iodide and lead nitrate. And both of these solutions look like water. They're colorless and they're clear. By the way, clear is not a color. Just, you can have clear blue or clear green, but water is not just clear, it's clear and colorless. When we mix these, though, we get this yellow-orange cloud forming. The reason this looks like a cloud as opposed to just color forming is that this is forming solid particles. Those particles are large enough that they can deflect the light, and so we can't see through this portion of the solution anymore because it's a solid, just like you can't see through a cloud because of all the little water droplets in it. So anytime a solution gets cloudy, we have a precipitate, a solid that's formed. If we wait, that solid will settle to the bottom because it's more dense than the liquid. So what's going on here is in this solution that's being added, we have potassium iodide. And we talked about how solutions form. Here we're not showing all the little water molecules surrounding these ions, but we've got potassium ions and we have iodide ions, and they have separated and they're moving around in the solution. In the other solution, we have lead ions and nitrate ions. And so I have an analogy for this. It's one of my favorites. So this flask here is like a party, and here we have two ions going to the party together, and here we have two ions going to the party together. So I've told you before, I think of metals as being masculine, and then the nonmetals are feminine. So here's the guy potassium and his friend, who's a girl, iodide. But these guys aren't in a relationship, they're just friends, right? And so they didn't want to go to the party alone, because who wants to do that? So, they went as friends. And over here is Mr. Lead and Miss Nitrate, and they also went to the party as friends, okay? So what happens at the party? People mix and they mingle, right? And you meet new people. So what happens over here is that lead met iodide, and there was chemistry, right? I love you. Can you come to all my classes? Oh, that's awesome. Yeah, so lead and iodide really, really like each other, right? So they meet up and they're like, ooh, and they stay together. And they're like together the whole night. In fact, they're not mingling together. They found a couch on the back porch and they've been making out all night, right? They're just not even really part of the party anymore. They are there, but they're stuck on each other, literally, right? So that happened. So this is an insoluble compound. Why did that happen between lead and iodide? Potassium and nitrate met up and they're like, you're nice. No sparks, nothing. It's like, yeah, we'll just hang out, chat, right? So why did these two stick together and the other ones didn't? Well, that's complicated, right? Just like human relationships are complicated. You set two people up, you think, oh, these people really like each other. And they go on a blind date and they're like, ugh, right? But other times you'd see these people that you're like, I don't know why they like each other, but they do, right? It's complicated. And we have that list of solubility rules that helps us to predict who's going to hit it off and who will not, okay? So any questions so far? So we're going to learn how to predict the products of precipitation reactions. So in this example with the lead nitrate and the potassium iodide. Here's the first beaker, we've got potassium and iodide, and here's the second beaker, we've got lead and nitrate. So these are the original compounds. And these are ions with electrical charges, right? And so you have to have a positive with a negative, right? So we can't have potassium and lead getting together because they both have positive charges and positive charges repel. Iodide and nitrate won't get together either. So there's two possible combinations. The combination that they came with, lead, I keep calling that lead, that's potassium. Potassium and iodide. But are they going to form a solid? No, because they came as friends. They came in solution. They're not going to form a solid just because there are other people around. And lead and nitrate aren't going to form a solid either. So then we have to look at, well, what happens if they swap partners, okay? So the lead and the iodide, the potassium and the nitrate. We look at the two possible products. And then we refer to our solubility rules and say, well, which of these, if either, is insoluble? We go through the solubility rules in our head, and the potassium, all potassium compounds are soluble, so that can't be it. And we see iodide is like third on that list of soluble things. Iodide compounds are generally soluble except with lead too. This is one of the exceptions. Okay? So then we can predict that this is the solid. So if there's no precipitation when you mix two solutions, that means there's no chemical reaction. There is a physical change in that these things are now mixed together. It's a physical change, but it's not a chemical change. And when you mix two solutions, precipitations do not always happen. Just like at a party, people do not always find their soulmate, right? Doesn't necessarily happen. You only get a precipitate if you've got insoluble compounds. So mixing potassium iodide and sodium chloride, think about, well, what would happen if we swap the partners? Potassium chloride and sodium iodide. Both of those combinations are soluble, no reaction. And so we can write out the reactants, but then we write no reaction, or oftentimes we're even too lazy to write that out, and we write NR. So there's one of those speed signs near my house, and occasionally it malfunctions and it says NR, which I'm pretty sure stands for no reading, but I always see no reaction. It's crazy chemist. So here's a list of instructions for how to write equations for precipitation reactions. You need the formulas for the two reactants, and below that reaction, write the formulas of the products that could form. And we'll do some examples, and I'll show you what I mean. Refer to the solubility rules to see if anything's soluble or insoluble. If all the products are soluble, you can just write no reaction. If anything is insoluble, then you need to finish the equation. Indicate the states of the product, solid or aqueous, and balance the equation. So those are the steps. Let's do some examples. Write an equation for the precipitation reaction that occurs, if any, when ammonium chloride and iron 3 nitrate mix. I'm going to try to go through this a little quicker because there's just so much stuff to get through. So if you need it slower, you can go watch the video again and again if you need to. So what we're going to do here is we've got ammonium chloride, and so that's ammonium ion and chloride ion. I need to look at the ions with their charges so that I can write the formula for that compound, ammonium chloride. Solubility rules tell me that's aqueous. Also, the reactants are always aqueous when you make these precipitation reactions. The other one is iron 3. So the 3, the Roman numeral 3, is the charge on the iron, not how many there are. So that's Fe3 plus, and the other ion is nitrate, has a -1 charge. So looking at the charges, I realize that I need 1 iron ion and 3 nitrate ions, and then that's going to be aqueous. And I'm leaving space here in case I need a coefficient. Now we're going to swap partners and see if any of the compounds that form are insoluble. So we're going to have ammonium with nitrate and iron with chloride. You have to have a positive and a negative. So I'm going to rewrite them over here, NH4 plus with NO3 minus, and Fe3 plus with Cl minus. Now, you could write the iron and chloride first, and the ammonium and the nitrate second, but we always write the guy first and then the girl, the cation and then the anion, just because convention, right? Mr. and Mrs. So now we look at this combination of ions. Is this compound going to be soluble or insoluble? Well, ammonium. Ammonium compounds are always soluble, no exceptions. So this one's soluble. So that one's going to be aqueous. And what about iron 3 and chloride? Well, chloride compounds are mostly soluble except silver, mercury, and lead. Is this an exception? No. This compound is also aqueous. So we actually don't need to write the products and balance the equation. We can just say no reaction. That's what you always hope is going to happen because it's faster. Any questions? So if I mix these two solutions, there's no chemical reaction that occurs, nothing new forms, it just gets mixed. Let's do another one. Write the equation for the precipitation reaction when sodium hydroxide and copper 2 bromide mix. So I need the formulas for the reactants, sodium hydroxide, sodium ion, and hydroxide ion. And based on their charges, I put those together as NaOH, aqueous. Copper 2 bromide, Cu2 plus, Roman numeral 2, and bromide. And so that's going to be CuBr2 aqueous. And then I'm going to swap partners to see if anything's going to precipitate. So, bless you.
Thank you.
Sodium with bromide and copper 2 plus with hydroxide. Before I go to the trouble of writing the formulas, I'm going to evaluate whether they're soluble or not. Well, this one has sodium in it. Anything with sodium in it is soluble. So that one's aqueous. And then copper 2 hydroxide. Well, hydroxides are generally insoluble, right? I didn't find any of the soluble cations up there, and the exceptions I'm looking for here, barium, calcium, and strontium. It's not one of the exceptions. So copper 2 hydroxide is insoluble. It's a solid. So that means I have a precipitate. I have to finish the problem. So NaBr, aqueous, +1 and -1 charges. And then Cu2 plus with hydroxide, I need 2 hydroxide ions to balance the charge on the one copper, and that's going to be a solid. And then I have to balance the equation. There's 1 sodium and 1 sodium. There's 1 hydroxide, and over here I have 2 hydroxides. So I need to put a 2 in front of sodium hydroxide. Well, that messed up the sodiums I just checked out, so 2 sodiums now, and over here is only 1, so I need to put 2 there, 2 sodiums, and then 1 copper, and 1 copper, and 2 bromides, and 2 bromides. And there's my balanced equation. Any questions? We're putting together a lot of the steps that we've learned. We learned how to predict formulas for ionic compounds, right? We learned how to balance chemical equations. We learned how to predict solubility of compounds. We're putting all of those things together here. Yeah.
So that bottom part where you're writing the Na charge.
This part?
Would that be the complete ionic equation?
That would be the bare bones of the complete ionic equation, yeah. And we'll get to that in a minute. Yep. So this part down here is like my work, my notes I made for myself, which is not technically part of the answer to this problem. But until you get really good at this, you should do that. It just makes it a lot easier to see what's going on. And then when we do ionic equations, it's going to be extra useful.